So
no one's died on my right hand side.
So, how many do we see here? How many are we concluding
I
here?
don't know. I'm confused.
We're saying 4? It's 4,
Why?
yeah.
Can you explain?
Because the two in the middle do not see identical things on either side. It's not an exactly symmetric molecule because there's not an OH group on the left side.
Yeah, but can the carbons in the middle see what the N carbons see as well? So
Yeah, they will all the way down the line.
No.
I'm confused.
Okay,
So
you draw what you think.
I understand what you're trying to say. I feel like it's just the lines that mess up with the idea.
These are hydrogens we can pretend.
Yeah.
Cool. So does this carbon also see this?
It does, yeah. It
Yeah.
sees everything connected to it all the way. It follows the paths of all the bonds to see what's connected all the way down the line.
And it also sees that.
Yeah.
And it also sees that.
Yeah.
Yeah.
Which is different from the other
To
side.
what that one sees.
Yeah, exactly. Yeah.
Because okay.
Yeah. Thank you.
Use them.
Good question. So that's why there are 4
I would
unique
rather
carbon
understand
environments.
than not.
Okay, next shape here we got like, what do you think here? Butane
I'll
2
follow the masses. Before.
4? Yep, looks like 4. Next one?
3.
Yeah, 3. Looks like 3. What about G?
3.
No, 2, 4. No, wait,
3.
Yeah, 3.
The 2CH3 groups.
Yeah, it's kind of tricky. There's 2 identical methyl group environments, right?
Yes.
All right. And H?
5.
That looks good. Yeah, that's a tricky one. Good one. And last one. Well done. Awesome. So we got the basics done. What I'd like you to do is assign the peaks on the spectrum to specific carbons within this structure. This looks to be, 1, 2, 3, 4. It's some sort of butanol. It's 3-methyl. Oh, I got the name on the screen. I was trying to name the structure. Okay, 3-methyl butan 1-ol. Can you take a couple of seconds just to figure out, okay, which carbon's more deshielded?
Wait, so
Yeah.
the height of the line
Yeah.
doesn't matter, right?
Yeah, you're right. The height of the line doesn't really matter, no. It's the fact that there are 4 carbon peaks. That tells me there's 4 carbon environments. And can we match each peak to one of the carbon environments in the structure? So take a couple minutes to scribble out which carbons correspond to which peak.
I'm not entirely sure.
Okay. When we take it up, you'll see. Basically, remember, the more electronegative or electron withdrawing groups we've got there, they're going to pull electrons away from those carbons nearest or connected to those groups. So we have an OH group bonded directly to one carbon for sure.
And the O is more electronegative than the carbon.
Yeah, yeah.
Yeah.
It's the second most electronegative on the table. So the oxygens are withdrawing from the nearest carbon. So that carbon there is going to be really deshielded, and it's going to be downfield. It's located downfield on our spectrum.
Oh, so the point of this is figuring out which carbon corresponds to which peak.
Yeah.
But why is it the second most?
Fluorine's the most electronegative.
Oh, I mean like the most electronegative in that.
Yeah, by far it's the most electronegative. Yeah.
Yeah, no, I was confused. I'm like, where the hell is fluorine in that molecule?
There's a secret carbon. No.
Yeah.
Okay, so this one's pretty short and simple, just because for the most part it's a fairly straightforward molecule where the carbons closest to the OH group are going to be more deshielded and downfield, right? So 30 seconds, then we'll take it up. Say they're going downfield. Well, I guess there's going to be a center line. It's
That one. The one that's not That's what's the
All right, let's take this one up. So I'll redraw the shape with carbons clearly defined in our structural diagram. So here we go. Here's the structure of our compound. So I'm going to call this carbon 1, carbon 2, 3, 4, 5. Okay, so this peak around 60 ppm, the one that's most downfield, which carbon would create a peak like that? Yeah.
Carbon 1.
Yeah, the one located right next to the OH group. This one right here. Perfect. And then the one that's next most downfield, around 40 ppm. Yep. Yeah, number 2, just working down the line, right? And then the one around 25 or so ppm. Yeah. Yep.
That one's 3, but can't you group 4 and 5 together?
Exactly. Yeah. Yeah. They will be because we have 5 carbons and only 4 environments. So you're right. This one here is carbon 3. This is the peak here at 25 ppm, and then the peak around 20 ppm. It's a bit higher, and that's why I was saying last lesson that the height of the peak doesn't really matter, but it actually kind of does because the height of the peak is influenced by how many carbons are within that environment. So a higher peak tells you there's probably more carbons in that environment. Yeah, the 2 terminal carbons here are causing this peak here around 20 ppm. They're the ones furthest away from the OH group, feeling the effects of that deshielding the least. Cool. And here we go. That makes sense. So here's the answers there. You see that lines up with our guesses. Cool. I got one more for you. Okay. So once again, I'm going to put up another molecule with a spectrum, and please assign the peaks. This is a 2-methylbutan-2-ol.
If it's downfield, it's deshielded.
That's right. Downfield is deshielded.
Downfielded, I like that.
Downfielded.
Garfield's cousin.
Can I check something?
Sure.
So the 2 carbons, the 2 methyl groups coming off of the carbon closest to OH,
Yeah.
they don't see the same thing.
They do.
They do? Why? Because one's, I don't think I'm quite understanding this.
They're both seeing, if they both see that they're both connected to the same carbon, that carbon's connected to, whatever it is, but they're both seeing that everything past that carbon, they're seeing the same.
So,
You have to remember in 3 dimensions, and with the rotation of bonds, they're going to see the same thing.
so the reason that this carbon does not see the same thing as this carbon is because this is so thin away and isn't shaped like that, right?
Say that again?
So the reason that this carbon doesn't see the same thing as this is because the shape of what it sees is different, right?
Let's go in order. This carbon sees one carbon connecting to a carbon that's like the tertiary, like a bunch of things connected to it. This one immediately goes to a carbon connected to different things. So yeah, they're both bonded to a carbon, but they're different carbons because they're bonded to different
And
things.
this one sees that going that way and that going that way, and there's no other carbon that sees that either, so that's the second environment.
Yep.
Then we've got this carbon which sees 2 things and 2 things, which is not what this carbon sees, so that's the third environment. And then these guys see the same thing because
They can,
they're
it's clearly this
both.
one, nothing else.
No, surely because that one's
But I did like
also
30,
seeing that one. I know this is the same thing's happening that way as well, but I thought which side it was on meant that it saw a different.
Because these bonds rotate, remember this whole thing just rotates in 3 dimensions, right? Along the bonds. This isn't fixed in this position. But they do see
It's
the
just,
same thing.
so, okay, right.
Because they'll both look inwards, see that carbon, see that it's bonded to that, and both see that
I'm assuming it
this
doesn't.
is connected.
So they both
He's
see
done it.
that there's 2 carbons, and they both see that they're connected to this,
see-
and they both see that that's happening,
2
and
years
that's
ago.
happening,
Yeah.
and that's happening.
Oh,
Okay, so this is-
Okay, let's talk about which peaks we assign to which. So this is what classification of an alcohol? Is it primary, secondary, or tertiary?
tertiary.
Yeah, okay. So right away, I noticed a difference when I looked at this because if you remember the compound we looked at before, this 3-methylbutan-1-ol, what type of classification would you give this alcohol? Primary, right? And look at where that carbon is, the one that's connected to the OH group. Its peak is around 60, right? Where is that carbon in this structure?
Around 70.
Why is it more deshielded?
Wait, which carbon were we referring to?
The carbon bonded to the OH. It's moved from a primary alcohol from around 60, and in this tertiary example, it's more downfield. It's more deshielded at 70. Why is it more deshielded in a tertiary case versus a primary case? Yeah, Ben.
Is it because the carbons it's bonded to is slightly more electronegative than hydrogen?
Kind of, that kind of makes sense, but also the bond length is longer. I was saying earlier those H's really shelter it. And with the primary,
isn't the carbons bonded to because the carbons bonded to hydrogens, they become slightly more electronegative than the carbon is bonded to the carbons, don't they? Because
not really.
Well,
No.
they're getting the electron from the hydrogen, whereas the carbon bonded to the other carbons isn't. So it becomes.
The overall charge of that carbon
Well,
is
no,
different.
There's a very slight
because you look at the
charge on the
carbon
carbons
bond
of
alone, you
hydrogen.
don't look at the carbon bonded to the methyl group. You look at the carbon bond
Yeah.
alone.
And that carbon-carbon bond length is longer. It doesn't have, here in the primary case, where there's two H's bonded to that carbon next to the OH group, right? Here, it's a CH2 group on that primary, right? So those H's shelter this carbon a little bit more than when that carbon is a tertiary and those H's are gone and replaced with longer carbon-carbon bonds. So here we've got it more deshielded. So let's go back to classifying the carbons in the peaks. So that carbon bonded to the OH is obviously the one at 70 ppm. And then what's the next peak? So we got the next peak around 35 ppm.
Yeah, I was
What
wondering,
has
does
created
that one
that?
have to be CH2 because it's shorter? So the other two that are closest are the same carbon environment, so they must be the big one. But why is it that the CH2 feels it greater than the...
Oh, maybe somebody else can help us answer this. That's a really good question.
I mean, I put CH2 for that one because I thought...
And that's good intuition because you saw the higher peak, which means more carbons in that same environment. But why is that CH2 carbon more downfield than those CH3s? That's your question.
Peak doesn't matter.
Come back to that. Ben.
Is it because the CH2 carbon has one less hydrogen, therefore the carbon-carbon bond lengths are longer, and therefore there's less shielding?
Yeah, there's less shielding. It has less hydrogens because you have CH3 versus CH2. Fewer hydrogens, less shielding, right?
Oh, okay.
Makes sense. No, I don't.
Yeah, alright.
The height of the peak doesn't matter.
And then like 5
But
minutes
no,
later
yeah.
we went.
The height of the peak matters.
He said why. The height of the
That's
peak
what I
has a
meant.
little impact.
Yeah.
That's the height of the peak
That's,
matters.
yeah, change your notes to a height peak doesn't matter except when it does.
So, what
The
I,
answer will always be yes unless
Pretty
no
much.
is required. Yeah.
guys, what I mean is that if you had, like, let's say you had a compound with 5 carbon environments, and you had 1 carbon in each environment, all the peaks wouldn't be at the same height, just due to, like, I don't know what, but they're slightly at different random heights. But that's an example where you have 1 carbon per environment, right? But here you distinctly have different numbers of carbons in different environments, so you do have drastically different heights as well, but it's not just due to like randomness, it's due to the fact that you have carbons in the same environment. Okay, so we assigned the peaks. We found that those methyl groups, because they're better shielded with those extra protons or hydrogens that are nearest the carbons, are better shielded, so they're more upfield. And then we have the carbon furthest away around 10 ppm. That's
Okay,
pretty
so
fine.
you would call both of those methyl groups carbon 3, just because of the same.
Yeah.
So if I was doing like naming, it would be the same as well?
Yeah, I would say that like the branched methyl groups, you might want to say, the branched methyl groups, if that's how you want to refer to them.
Do we still call naming nomenclature?
Yeah.
What? The ITN numbers, I assume that's relative to the height of the peak.
Yeah,
What is that
intensity.
intensity?
Intensity. It does matter. You're giving it a name, it matters.
There you go.
Do we need to know, are we given these numbers?
You don't need
Why
the
do we need
intensities. You'll be given a spectrum like this, and there'll be a discernible difference in peak heat, peak height,
Peak heat. I like
peak
that.
height,
Peak heat.
if there are multiple carbons in the same environment. Cool, and sweet. Like that's a huge difference. You don't need to know the intensities; they're not really useful. Just by looking at it, you can tell. But what we've done, without looking at the table that we used last time, was intuit. Is that a word? Intuit? Yeah. Intuit? I might have been emphasizing it wrong. Intuit the positions of peaks based on how shielded or deshielded they are, just by thinking about what the structure looks like and how they're influenced by the atoms around it. Great job. That's awesome. So that table is kind of useful, but kind of like you don't need it now. You've gone from the
Beyond it.
Padawan to the master, if you will. There you go.
Okay, bye, Sam.
Okay. Last example I want to show you before we get to doing some work on your own is pentan 1-ol versus pentan 2-ol. Okay? Kind of similar spectra, but once again, the effects of the number of hydrogens there are and influences the positions of the peak. So pentan 1-ol, pentan 2-ol, very similar. Last class you might have been like, these spectra are too similar, how can I tell them apart? But looking at this, looking at which carbons, the numbers tell you which are assigned to which peak. So number 1, this is 1, then 2, 3, 4, 5. Same with the upper graph. 1 is more downfield all the way to peak number 5, which is upfield. We can see that for pentan 2-ol, that first peak makes sense. But the second highest peak, the one at 40, is caused by this carbon there, not the end carbon, not carbon number 3, right? Because it only has 2 hydrogens bonded to it, whereas the carbon at the end of the chain has 3, so it's better shielded. So that's why that one at the end of the chain is more upfield. Make sense? Cool. So I've got a couple tasks for you. The first one is to complete the worksheet here, where once again I'm going to Solomon. I've given you a few spectra and a few compounds. The carbons are not labeled. What you need to do is label or assign the carbons to each peak on the spectra, so it's extra practice doing what we just did. And the second thing I'd like you to do as a creative exercise is go to this fantastic website. If you Google that, or if you go directly to the link for those who are on the slides right now, you can search for a variety of organic compounds. You can open up NMR spectra for any of these compounds you find, and assign peaks to them as practice. So you can look at more interesting compounds than what I've got on this worksheet, and really interesting large ones if you want, really challenging ones, and see if you can match up all the carbons in the molecular structure to the peaks you see. These are real spectra. So this is a database of like samples people have run, and they've generated NMR spectra, so the Y means yes, there is a NMR available. There's mass spectra as well, which we'll get to next week. There's IR spectra you can look at and get some practice at too. How it works is you either put in the compound name in the box or the molecular formula. And I think the molecular formula option works the best. So you could look up like C2, or no, C5, H12O, like I did, and come up with all the different isomers of that formula, like 1-pentanol or pentan 1-ol, which we were just looking at, along with a bunch of interesting ones. And by looking at all those isomers, you can get some practice assigning peaks. Sounds cool? So the first thing we're doing is a worksheet. The second thing is more of a creative exercise, bit of exploration of more interesting compounds. Awesome.